Alright guys, so welcome to this mass balance tutorial here. So this isn't a problem taken from a textbook or anything like this. This is actually a problem that I've designed myself. It's a relatively simple mass balance problem. It goes like this. It says a two-stage process is used to recover 95 weight percent methanol solution. The feed stream contains 40 weight percent methanol and the balance water. The feed enters a flash drum where a vaporous methanol-rich stream is produced and sent into a distillation column. 100 kilo per hour pure water stream also enters the flash drum for temperature regulation. The bottom stream for the flash drum is 96% water. The distillation column has a bottom stream of pure water with a mass flow of 225 kilos an hour, and 95% of the methanol in the feed is recovered in the distillate stream. Please determine all the mass flow rates and compositions in this process. In doing so, please produce an initial degrees of freedom analysis, write out the equations and calculations you develop in solving for the unknown values, and produce a labeled mass flow block diagram showing flow rates and mass compositions. So, as I say, this is a relatively simple mass balance problem, first of all, because there's no reactions going on in our system, or we can assume that there are no reactions going on in our system here. You've got methanol and water going in, and you've got methanol and water coming out. It's a case of determining the mass flow rates and compositions of the streams. For a problem like this, I'd generally recommend that students start off by diagrammatizing the problem. We've got two units here, a flash drum and a distillation column. So here is a diagram that I made earlier. And as you can see, we've got our flash drum, we've got our distillation column, we've got all our streams here denoted with arrows. It's kind of a case of filling in the blanks now, I'd say. So let's have a look at our problem statement again. It says the two-stage process recovers 95 weight percent methanol solution in the distillate. So that's basically saying this distillate here, you've got 95% methanol, and then that would mean you've got 5% water, right? The problem statement then says from a feed stream containing 48% methanol and the balance water. So down here, we've got 40% methanol and we've got 60% water. The problem then says 100 kilos an hour pure water stream enters the flash drum for temperature regulation. So we can delete this and we can say we've got a pure water stream that is 100 kilos an hour. The problem then says the bottom stream for the flash drum is 96 weight percent water. So let's just add that to our mass compositions here. The problem then says the distillation column has a bottom stream of pure water. So let's add that to our diagram. And it has a flow rate of 225 kilos an hour. The problem then says 95% of the methanol in the feed is recovered in the distillate stream. So that isn't necessarily something that we can add to our diagram, but it's certainly something that we can mathematize, right? 95% of the methanol in the feed is recovered in the distillate stream. So that's basically saying of the methanol that enters via M1 here, 95% of it leaves in M5, right? So how we could describe that mathematically, we could say 95% of the methanol that enters here, which we could describe as 0.4 M1, is equal to the methanol that leaves in M5, so 0.95 M5. And conveniently, we've got 0.95s on both sides of our equation here that we can just cancel, right? We can divide both sides by 0.95, and that leaves us with 0.4 M1 equals M5, which is a nice and simple mathematical idea. Okay, reading the rest of the problem, it says, yeah, please determine all the mass flow rates and compositions in this process. We've gone ahead and done that. The only kind of gap I'm noticing here is with M3. We don't have the values here for our mass compositions, and so we can just assign it an unknown label. So let's just call the mass fraction of methanol in M3 X, and by the same token, the mass fraction of water in M3 1 minus X, in the sense that, you know, if the mass fraction of methanol was 0.3, then the mass fraction of water would be 0.7 or 1 minus 0.3. Okay. The problem says produce an initial degrees of freedom analysis. I would expect students to do this even if they weren't asked to, okay, because the degrees of freedom analysis can kind of establish whether the problem is solvable, or at least what parts of the problem are solvable. There are three degrees of freedom analyses that we can carry out on our system here. So the first is on the flash drum. So for our flash drum, we would only consider streams M1, M2, M3, and M4. We can carry out a degrees of freedom analysis on our distillation column, and for that we'd only consider streams M3, M5, and M6. And naturally, we can carry out a degrees of freedom analysis on our system as a whole, and for that degrees of freedom analysis, we consider M1, M2, M4, M5, and M6. Or in other words, we'd only really neglect M3 because that's taking place within the overall system. Okay, we're only considering the streams that are entering or leaving the kind of bounds that we're drawing here, these kind of red bounds. Let's start with our flash drum then. So we can say degrees of freedom on our flash drum is equal to, so we want to establish how many unknowns minus independent balances minus other relations here. So how many unknowns do we have? We've got M1, we've got M3, we've got X, and we've got M4. So that's 4 unknowns there, minus 2 independent balances, one for the methanol, one for the water, right? And we don't have any other relations to consider here, and so we've got 2 degrees of freedom on our flash drum. Since we've got 2 degrees of freedom on our flash drum, that basically means that the flash drum is underspecified. We need more information to be able to solve through on our flash drum, probably. So let's move on to our distillation column. So for our distillation column, we can say we've got 1 or M3, X, M5 as our unknown. So that's 3 unknowns, right? We can still say we've got 2 independent balances, one for the methanol, one for the water. And we've got 0 other relations. So that's 1 degree of freedom. So the distillation column is still underspecified. Let's move on then to our overall system. So for our overall system, we've got M1, M4, M5, and that's it. So we've got 3 unknowns minus 2 independent balances, one for the methanol, one for the water, minus an other relation. So the other relation is this idea that we established earlier. 3 minus 2 minus 1, that gives 0 degrees of freedom, and so we need to carry out a mass balance on our overall system. Let's move our degrees of freedom analysis over into the top right corner here, just so that it's out of the way. And let's take this equation that we established earlier, this 0.4 M1 equals M5 idea. Let's call it our recovery equation. And now let's move on to doing a mass balance on the water. So we want to consider water that is entering our system, and we're saying that that is equal to the water leaving our system. So how can we describe the water entering our system? Well, we've got 60% of M1, and we've got this pure 100 kilo an hour water stream here. So let's go ahead and add that in. So that's the water entering our system. How could we describe the water leaving our system? Well, we've got 96% of M4 here, plus 5% of M5 here, plus all of this 225 kilos in our stream here. So let's just write that down. Okay, let's move on to our methanol mass balance here. So we can say going into our system, it's just this 40% of M1 here. And leaving our system, we've got 4% of M4, 95% of M5, and nothing here. So let's write that down. Okay, so it's almost like we've got 3 simultaneous equations here, to use the kind of mathematical language, with 3 unknowns, M1, M4, and M5 here. Okay, now my personal view to kind of solving through with this problem here would be to make use of this recovery equation here to substitute M1 for M5 in both of these equations here. So we note that we're saying 0.4 M1 equals M5. We could directly put M5 on our left-hand side here, and we could put 1.5 M5 on our left-hand side for our water balance. Okay, so let's just go ahead and do that. Okay, I'm just going to scroll down here. So we've generated these 2 equations. I note that we can kind of simplify them further. So for our first equation here, we could subtract this 0.5 M5 from both sides. We could subtract this 100 from both sides and simplify that way. And yeah, with our second equation here, we could subtract away that 0.95 M5 So let's just go ahead and write this out on our left-hand side here. Okay, so these are our kind of simplified equations here. Now, note, I mean, we could simplify our second equation even further by saying 5m5 equals 4m4, but I'm not going to do that here. The way I see it, there are, well, first of all, we have two linear equations here, right? My preference for two linear equations would be to use the elimination method. There are two kind of options here. The first one would be to multiply the second equation by 29. That would mean that our m5 coefficient would be equal to this m5 coefficient, and so we could subtract the equations away. Or the second option might be to multiply the second equation here by 24 to make this m4 coefficient equal to 0.96. And so again, we subtract the equations from each other, the m4 terms will eliminate each other, and we can solve through for m5. I reckon the second option is probably easier there, so let's go ahead and do that. I'm just going to label up our equations here. So let's call this equation 1, let's call this equation 2, and let's say equation 3 is equal to equation 2 times 24. And so we can say 1.2 m5 is equal to 0.96 m4. I'm then going to subtract this equation 3 from our first equation here. And so we obtain 0.25 m5 equals 125. Because we note that the m4 terms have eliminated each other. 0.25 m5, this is kind of solvable by inspection. If we multiply both terms by 4 here, which gives us 500. Now, if we're saying that m5 is equal to 500, I can certainly go back into my mass flow block diagram here and just replace m5 with 500 kilos an hour. If we're saying that m5 here equals 500 kilos, then we can say that m3 by inspection is 725 by just doing an overall balance here. To solve for m4, we could look back on the equations that we generated earlier. We said that 0.05 m5 is equal to 0.04 m4. We could rearrange this then and say that m4 is equal to 5/4 of m5. And therefore, by inspection, m4 is equal to 625 kilos an hour, which we can then add to our diagram. And then again, by inspection, we can say that m1 is equal to 1,250 kilos an hour. And we're almost done. Note that we still need to calculate for x here, which is the mass composition of methanol in m3. The way I see it, there are two different ways that we can do this. We could do a methanol balance on our flash drum, or we could do a methanol balance on our distillation column. The way I see it, it's probably simpler to just do a methanol balance on our distillation column, because again, by inspection, we can just say 725x is equal to 95% of 500. So let's just write that down. So we're saying 725x is equal to 95% of 500. We could divide both sides by 725 then, and say that x is equal to 95% of 500 over 725, which gives us a value of 0.655 for our mass fraction of methanol in M3 here. Let's just update the mass flow block diagram. And there we have it. We've got our labeled mass flow block diagram. We've shown all the equations that we've used to solve through for our mass flows and mass compositions. And of course, we've carried out degrees of freedom analysis. We've done everything that the problem's asked. Excellent. So there you have it. If you have any questions or comments about that problem, please feel free to leave them down in the comment section down below. Otherwise, thank you very much for watching.